Okay, wow, what an intro. Thank you so much. For anyone who has to leave when the hour comes, feel free. I didn't expect such a warm and amazing intro, so thank you guys. Yeah, so I'm Anthony, and these are my advisors, Fulkit and Alberto. And thanks to you all for coming. I'm excited to share a bit about my research on using machine learning to make robots better at rearranging the world around them. So we can quickly start by reminding ourselves where robots are today. If people think in the audience, what are robots out there doing, performing tasks? You might be imagining your classic automotive assembly line with arms that are kind of repeating the same motions over and over again very rapidly. And because those environments are highly structured with all details known ahead of time, those robots don't need to perceive or think much about what's going on in the environment. And where we would like to go is to enable robots to provide useful value in domains with less and less structure. So with that in mind, the big idea that I've been interested in this thesis is enabling robots to perform useful tasks in environments with less structure, like households. Imagine systems that can clean up rooms or declutter countertops and desks, or use areas like cabinets, shelves, and hooks to put objects away. And this is, of course, quite a diverse range of tasks, but one common element that many of them require is for robots to actually look around at objects in the surrounding scene and perform actions that rearrange those objects relative to other components in a way that achieves some underlying objective. This problem class of scene rearrangement has become recognized by many in both the robotics and machine learning communities as an important problem class to tackle, precisely because it places this strong emphasis on the interplay and coupling that exists between perception, planning, and geometric understanding. So if we want to build robots that can perform these kinds of tasks, then we must make progress on making scene rearrangement abilities more and more general. And to further motivate my research in this area, I want to show this amazing recent video from this new startup company called Figure. They're building robots with the similar goals in mind, and they made this demo of their robot picking up this cup and plate and putting it in a dish rack. And while I think this is like an amazing example of the kinds of rearrangement abilities that we're after, working in the real world, I just want to point out that we only saw it happen kind of in this one scenario with this one set of objects. And you can think for yourselves, what are all the other ways that this task might have gone? And just imagine how much harder it would be to enable the robot to generalize to all those different scenarios. Objects can have different appearances and shapes. They might only be upright during a training phase and then suddenly become sideways during deployment. And it's just very costly to manually collect data in all possible scenarios. So we first want our robots to acquire knowledge and skills that generalize in those different ways. Now, today's paradigm for obtaining that kind of generalization is to train giant machine learning models on an immense amount of data and hope that with enough scale, that kind of generalization will start to emerge. And people are definitely making super exciting progress in that area with large-scale data collection efforts and more intuitive interfaces to be able to collect the data. But no matter how big of a data set you have, there still might be edge cases and scenarios that confuse the system at test time. So we also want to consider what it might look like for robots to acquire new concepts and skills as needed by specific environments that are encountered, and in a way that makes it easy for whoever has to program these machines. This is more vivid in people's minds these days with advancements in foundation models, where you can teach all kinds of new tasks on the fly just by prompting with a few examples. So we also want to wonder what would it look like for that same ease of programming a new task or skill to be possible with robotic manipulation. Over these past years, I've developed a few methods and demonstrated their effectiveness toward achieving these goals. So one line of work leverages equivariant neural fields to enable both data-efficient imitation and generalization across object categories. The other line of work uses SE3 pose diffusion models that operate on 3D point cloud pairs, and these handle multi-object scene variations and multi-modal solution spaces. So for the first part of my talk, I'll discuss some details on these works. I'll first introduce our work on neural descriptor fields, and then I'll discuss relational pose diffusion. And that first part mainly focuses on using perception information to make predictions and have the robot sort of imagine plans for possible ways that objects in the scene can be rearranged. Then in the second part, I'll finish with some more recent work focusing on how we can improve online execution ability by incorporating closed-loop control. So for part one on rearrangement prediction, we'll set up our technical problem statement and assumptions a bit concretely. For this part, we assume that a robot observes a scene and its own internal state, and must predict a 6-degree of freedom transform to then apply to one or more objects in the scene via pick and place. We also sometimes include a prediction of some particular way to grasp the object, while in other cases we'll use separate grasp generators. And tasks will be specified via some offline set of demonstrations, and these encode what kind of predictions the system should make. So with that setup, we'll make some common assumptions for the next few projects. We assume objects are rigid, and we have access to 3D point clouds, which are currently obtained from calibrated depth cameras. We also assume some ability to segment the object instances from the point cloud. Usually that's on the single manipulated object that's being moved. And then when we execute our task with the robot, here we'll assume objects never move after they've been grasped relative to the hand. And we use off-the-shelf inverse kinematics and motion planning tools to plan paths, which are then executed open loop. Now to begin, I'll talk about our work on neural descriptor fields. This is an SE3 equivariant object representation for data-efficient manipulation. Just to give a teaser of the result that we enable, suppose a robot is provided with a demonstration of grasping this upright mug and then hanging it on the rack. Our system and representation can use just a small handful of these demonstrations to repeat the task on a new mug that has a different shape and is placed in a never-before-seen pose. More generally, we're proposing a representation that enables observing just a few examples of pick and place and generalizing the execution to novel objects in out-of-distribution poses. So now we'll take a bit to understand some intuition and motivations on the technical aspect of our approach. So to get started, let's first assume that we have some demonstration and test object, here a mug, and that they're identical. Something we can do is we can attach a body frame to the object, then record the grasp pose in that frame, and then estimate the pose of the mug in its new configuration. So the grasp can be executed just by moving to that recorded grasp pose, but expressed in that new estimated frame. But when the mug has a different shape, this procedure will fail. Because the gripper has to align to a local feature, like the rim in this case, and that feature actually changes location on the new shape, we must instead attach a local reference frame that moves with that task-relevant feature. Then moving to our demonstrated grasp pose, but expressed in that corresponding local frame on the new instance would properly align the gripper to the rim. However, the local feature to use is specific to a task. So we need the ability to attach these local frames at different geometric features on the object. For instance here, if we now want to place a mug on a shelf, we can attach a frame to the bottom of the mug, then detect the corresponding frame and align the shelf with the bottom of the new mug. So overall, what we're after is a representation that enables corresponding any local coordinate frame, and we would like to train this representation offline without any task-specific data. Then we want to use demonstrations to obtain a specific coordinate frame that's attached to a geometric feature that's relevant for a task, and use the representation to generalize the task by detecting that corresponding frame on new objects. So that's kind of the intuition, and I'll now describe some of the technical aspects of our approach. So for the NDF project, in addition to those common assumptions that I said at the beginning, we'll assume that there's just a single manipulated object. The position, orientation, and shape are all unknown ahead of time, and we represent that object as a segmented point cloud. We also suppose that the desired task is demonstrated using no more than, say, 5 to 10 demonstrations. And we assume this object comes from a known category of models, a category of shapes. And for that category, we assume that we have an offline data set of 3D models. In this project, we use ShapeNet. So we'll first propose our neural point descriptor field. This is a continuous function parameterized as a neural network. It takes in as input a 3D point X and a point cloud P, and it outputs a descriptor vector. So this descriptor is meant to vary depending on the 3D location of X, and it's meant to encode information about the spatial relationship of this point to the geometric features of the object. So that's shown here in this kind of toy visualization where I'm going to move the point around, and this output vector represented as these colors changes. So what properties do we want in this field function? First, for our goal of correspondence matching, we want the descriptors to encode this information in a way that's consistent across instances from a category. This would mean that points near similar geometric features map to similar descriptor vectors. We find that occupancy networks trained for 3D reconstruction learn intermediate features that are consistent across shapes in a category. So more specifically, given the offline data set of 3D models, This network is trained to take in a partial point cloud of the object, along with a query point in the vicinity of the object, and predict the likelihood that the query point is inside or outside of the shape. By training that same network on a full category of shapes, the learned representations vary smoothly and consistently across the different shape instances. So based on these findings, we parameterized our descriptor field as a function mapping a 3D coordinate to the intermediate activations of a point cloud conditioned occupancy network. And I'll quickly note, there's more recently developed techniques showing how other kinds of descriptor fields can be obtained in other ways. For instance, William here at MIT did some awesome work using distilled features from foundation models, and I think that's like a really exciting advancement in this area. So in this work, we're using point cloud conditioned occupancy networks for the pre-training phase. Great. But let's now consider what might happen if the object is presented in a different pose. We know that this is the same object just rotated, but to the neural network, it looks like a completely different point cloud that maybe it's never seen before. And so if we naively use those features as descriptors, then rotating this mug could lead to a new descriptor, even though the point we're querying is still near the handle of that rotated object. What we would like instead is for our descriptors to be invariant to any joint transformations of the object and the query point, since we know that point maintains the same position relative to the object. In other words, we want transformations of the object to lead to a corresponding transformation of the descriptor field, and we specifically desire for this field function to be SE3 equivariant. Mathematically, it means that for any SE3 transform T, that if we transform our query point to get a new point Tx, and similarly transform the point cloud, here shown as Tp, that our output of the field function remains unchanged. So we obtain this approximate form of translation equivariance by operating with mean-centered point clouds. And for rotation equivariance, we incorporated vector neuron layers into our point cloud encoder. There's lots of options out there these days for building equivariance of different kinds into neural networks. And so there's potentially other choices that we could have used, or more new options that are available since we did this work. But the vector neuron layers were quite straightforward to plug into our project and provided performance that met our requirements. Now with this construction, transforming the point cloud and the input jointly leave the descriptor unchanged. So we have these properties, and now given a reference point, we would want to obtain the corresponding point for a new shape. We'll set this up as an energy minimization problem, where energy is defined as the descriptor difference between 2 points. So different points lead to different energy values, and considering these descriptor distances throughout the whole region, we obtain this continuous energy landscape, which can be optimized to find a minima corresponding to the reference point. Here I'm illustrating this energy landscape for both mugs and bowls. So target points on the demonstration point cloud are shown in green, and the inferred corresponding point for new shapes is shown in blue, and that's at the minima of that energy landscape. Due to equivariance of the descriptor field, rotations and translations of the object lead to corresponding transformations of that landscape. So that's what we wanted. Now, what if we want to go beyond individual points and model correspondence over local coordinate frames that have an orientation? We can achieve this by concatenating descriptors of a set of points that move together as a rigid body. So different transformations of this point set, again, lead to different descriptors, but now concatenated. And thus we here obtain pose descriptor fields, which represent SE3 poses of the point set, as well as any local coordinate frame that's rigidly attached to those points. Again, mathematically it's shown we have a set of 3D points, denoted calligraphic X, and we're showing how for this rigid transform big T, we can concatenate those little f point descriptors for each transform point to get our new pose descriptor represented as a big F. And again, given a new shape, with a new object with a different shape and orientation, the query point set placed in a similar configuration relative to the mug has a similar pose descriptor, again shown by the matching colors. Cool. So we have our goal of corresponding frames across instances and poses. Now we can try to use this to perform tasks like grasping. The way to think about it is we can attach an external rigid body, such as the gripper, to the query points. And in this way, there we go. The body frame defining the pose of the gripper can directly parameterize that local frame in the vicinity of the object. So we can therefore directly encode the gripper pose using our descriptor field. Now those descriptor distances induce an energy that can be minimized to obtain a pose that matches a demonstration. Here we're seeing that visualized. So we're optimizing over this pose T to find a pose such that the descriptor for t, conditioned on the new object, matches the descriptor we encoded in the demonstration. And I want to make one subtle but critical point regarding these query points and that pose of the external body. So first, we note that any rigid set of 3 or more non-collinear points can parameterize that gripper pose. But for our desired grasping skill to generalize the way we want those points to be sensitive to the features on the object that the gripper actually has to interact with. We achieve this by initializing points near the fingers on the gripper, since those are the points, the gripper parts, that contact the object. And by placing query points near contact locations, we encode the geometric features that have to be detected to allow the robot to make the same kind of contact on that new shape. And our heuristic for implementing that was to sample query points uniformly in a bounding box of the gripper fingers. And note that we can attach arbitrary external rigid objects to those query points. So I'm again showing it for the gripper as I've been discussing. But on the right, we see that, we see that same idea, but for a rack, whose pose is being optimized to obtain a relative configuration for performing a hanging task. And just to drive the point home, when we encode those demonstrations of hanging a mug on a rack, we're now encoding a different task-relevant part on the object, which is the handle instead of the rim. And this is achieved by utilizing knowledge about the hook on the rack to obtain query points that are sensitive to the handle. Cool. So let's look at some videos. Here's some real-world examples of manipulation tasks enabled by our approach. We're again going to see some examples of hanging a mug on a rack, where the execution is on objects in poses that were really different than those in the demos, as well as having different shapes. Here there's going to be some more examples of grasping bowls by the rim, placing them on the side, and then grasping bottles from the side and placing them upright on this black shelf. So in summary, we propose neural descriptor fields. This is a representation modeling objects as 3D neural fields of descriptors, which encode correspondence across shapes, are trained via self-supervised 3D reconstruction, and are equivariant by construction. And these descriptor fields allow us to correspond local frames attached to geometric features that are relevant to a given task, extracted directly from demonstrations. And we show how we can use NDFs to perform pick and place on unseen objects in OOD poses from just a few demonstrations. So I was pretty excited about this because it showed me one way of generalizing across different shapes in a category and handling unseen positions and orientations of objects, all the while requiring just a small handful of demonstrations that can be provided quite quickly. But one limiting assumption was that there would only be a single object that changes its shape and pose. And this is something we aim to tackle in a follow-up project called relational neural descriptor fields. The goal now is to enable generalizable placing on pairs of objects, where both objects in the pair can change in their shape and pose, and still use just a few demos of the desired relation between those objects. So for the example of hanging mugs, which you'll see a lot of today, the result looks something like this. In the first example, we see the robot grasping this short mug and placing it on the rack, which is on the left side of the table and has the hook near the bottom. And then in the second example, it can figure out how to grasp the taller mug, which is presented sideways, and it infers how to place it on the rack, which is on the other side and has the hook near the top. The setup is almost identical as before, except now we have two objects, each with unknown shape and pose. So we now have a segmented point cloud of both of those objects, and we assume we know which segment corresponds to which object. So I'll just give a brief overview on how RNDFs are working. The main idea is to represent the pair of objects independently and leverage one NDF for each category to extract the task-relevant parts that align with each other in the demonstrations. We again assume that these relevant parts are those that interact to satisfy the relation. So in this example, the relevant part of this red rack is the hook, and the relevant part of the mug is the handle. The way we extract these parts from multiple unaligned demonstrations involves labeling a 3D key point in one demonstration to provide a reference, and then using the NDF representation itself in this iterative variance minimization procedure, which finds parts that are aligned in a consistent fashion across multiple demos. At test time, we'll then use the first NDF to find the corresponding task-relevant part on the first object, and similarly find the relevant part on the second object, but now we can express that pose on step 2 relative to what we found in step 1. So that's what allows us to represent the relative transform that can align these two parts. Here's some more videos of results that this enables in the real world. So here's now a stacking task of placing a bowl on top of a mug, and the shape of both of these objects was never seen before in the demonstrations that we provided, and I can kind of go in and vary the location and orientation of both of these objects, and it can still figure out the right way to reorient the bowl to achieve the stacking. Here's one more example of a task. Here we have bottles, and we want to have the robot place a bottle upright in this container. So again, unseen shapes. And we can place the bottle sideways. It can still figure out how to reorient the bottle and put it upright. And then right afterwards, I like to show this kind of silly example of even putting the container sideways and having the robot figure out what it might look like to place a bottle upright in a sideways container. I don't know why that would be useful, but it's something we can do. We also have a proof of concept showing RNDF enabling multi-step relational tasks. So here's that concept applied. We're first processing the mug to put it upright on the table. And then based on the result of that first step, the robot's going to look at both the mug and the bowl together and figure out how to stack the bowl on top of the mug, but in its new upright orientation. There's additional qualitative examples we have on simulated objects showing how relations can be chained together to rearrange multiple objects in a sequence. But I don't have too much time to get into that right now. So the main takeaways here are that we can use the descriptor field representation to encode pairs of novel objects and localize their task-relevant parts to solve for transforms that achieve a desired relation, again, just demonstrated from a few examples. And we showed this on 3 real-world rearrangement tasks, as well as a proof of concept on using RNDS for multi-step tasks by chaining relations together. So this is exciting. So now we can handle unknown shapes, and we can handle pairs of them, but there's still clear limits to the abilities that I've been showing so far. If we go back to imagining our home robot and think of the useful decluttering tasks that maybe they might help us with, it could be like putting dishes away in a dish rack, or putting away a bunch of textbooks and notebooks from a desk. Or in my running hanging example, the racks might not look like the one that I showed. They might be something more like this, where there's many possible places to perform the hanging operation. But looking at the tasks that I showed, they don't quite match the requirements of these tasks. And one major issue is they still assume a pair of singulated objects, rather than considering scenes that might have multiple objects, each of which might also have slightly more complex geometry. So in this next project, we wanted to consider scenarios like the following. What if there are multiple objects that make up an entire scene, and among those multiple objects, there could be several valid or equivalent geometric parts used for placing? And again, as a preview, here's a demo video of what this next method can achieve. We see that by processing this whole scene that includes multiple racks on the table, the robot can hang the mug on multiple of those available locations, both across the different racks and across different hooks on the same rack. So common assumptions are the same, and the setup is pretty similar. But now we suppose that there's just a single manipulated object as well as that external scene composed of multiple objects. And we represent that entire scene as a single point cloud, so we don't segment out any of the individual objects in the scene, just the manipulated object. We also here don't have any pre-training involved, so we instead directly learn from a set of demonstrations that show a variety of scenes with the manipulated object placed in a correct configuration in the scene, and then we'll test on pairs of objects and scenes that have never before seen shapes and layouts. And because of this, we use more demonstrations than before. We'll use about 1,000 of these placing demonstrations, and these are obtained using scripted policies purely in simulation. The key challenges to overcome from these multi-object scenes is that they vary combinatorially in the layout and shape of the individual objects that make up the scene. So on the input side, that variation presents an even greater generalization challenge, since things can change even more than before. As well as on the output side, it means that many solutions might exist for prediction. And furthermore, for planning and searching to find the pick-and-place actions that the robot wants to execute to achieve the desired placement, we need to keep in mind that there are certain geometric constraints of the robot that need to be satisfied. So for this part, that means we want to actually cover the space of all those possible placements at test time, rather than say, let's just converge to like a single mode, because that single solution might not be reachable when we actually consider the robot moving the object there. So we'll set things up from the most basic thing we could do. We'll obtain demonstrations of a point cloud that shows an object properly placed in a scene. And I'm going to call this the ground truth combined object scene point cloud. So the scene is this black bookshelf, and then the object is the blue book point cloud. We can create data for training a model to see an initial point cloud of the book in some random pose, and then predict how to return the book back to its correct configuration on the shelf. One of the first problems we'll run into if we do things this way is that there's no signal telling the model which among all possible open slots on the shelf should be used for prediction. And this is a common issue that many are familiar with in the field of learning from demonstration. And treating it naively can lead to the common problem of learning the average of all possible solutions. And that average tends to just completely fail at even fitting the data. So the key idea to overcome these issues is to train neural networks to perform iterative pose denoising of the combined object scene point cloud. Given our final point clouds that show the object properly configured, we can create multiple noised versions by incrementally perturbing the object pose, and then train a neural network as an SE3 pose diffusion model. This takes in the perturbed point cloud as input and iteratively predicts how to go back to the original configuration one step at a time. It's the iterative nature of the denoising with diffusion models that makes this a good fit for overcoming the difficulty fitting demonstration data containing multimodality. And that's again something that many in the robotics field are pretty familiar with these days with the recent success of, let's say, diffusion policies for learning controllers from demos that have multimodal behavior. So applying the same idea here. This approach conditions the transform prediction on both the object and the scene, but we find that the global information in the scene that's far away from the object can act as a distraction and hamper both the precision and the generalization. So building on that intuition, we modify the scene point cloud to only consider parts of the scene that are near the current object point cloud on a given denoising iteration. And we achieve that local scene conditioning by returning points in the scene that are within an axis-aligned box centered at the centroid of that imagined point cloud. So now we have a pipeline that processes the scene by cropping near the current object point cloud. It takes the index representing which denoising iteration we're on, and it passes all this to a neural network to predict a rotation and a translation. And these are applied to the object to obtain a new combined object scene input, which is used on the next iteration. We process the point clouds with a transformer to leverage attention within and between the object and the scene, but in the interest of time, I won't get into too much detail about training and architecture. And finally, we tried different mechanisms for selecting the crop size and found that processing the scene point clouds in a course-defined fashion leads to the best results. So what it looks like is that on initial iterations, we consider nearly the whole scene, but as the solution converges, we'll continually recrop the scene point cloud to a smaller and smaller local region near the object in its final predicted pose. So that formulation now allows us to run this model iteratively from a diverse set of initial guesses, and then have the predictions converge to a correspondingly diverse set of solutions that achieve that high coverage we were after. So here's some examples of what the denoising looks like for figuring out different places to put books on this shelf. Here's like a stacking task for cans, and we can find different locations for stacking on different cans or putting it in like an open region, and then figuring out different places to hang an object on different racks. And here's some more examples in the real world where now we have the robot performing pick and place. So you can again note that multiple of the available locations for placing were found. I'll just show that for a second, the different stacking locations. And I also want to emphasize watching the robot videos that it really was critical to obtain good coverage over the possible placements to ensure that the robot could select one that was feasible to reach, given the geometric constraints of the arm and like needing to avoid collisions with the shelf and things like that. Here's one more set of examples of placing a book on a shelf. You can find multiple of the available shelf locations. Cool. So the takeaways from RPDiff is that post-diffusion is a powerful way to handle multimodality and rearrangement among multi-object scenes, and that leveraging local geometric processing can be very beneficial for both generalization and precision when processing larger scale scene observations. And our results showed that we can use RPDiff to perform this kind of rearrangement among real-world multi-object scenes, and that the good coverage achieved by the predictions support motion planning and kinematic constraint satisfaction when executing tasks via pick and place. So that's what I have to share for this first part of the talk, toward the goals I introduced at the beginning. On one side, this research has contributed various insights regarding how different learning and representational techniques offer benefits like generalization and data efficiency. And at the same time, we've shown how these components allow robots to perform a variety of challenging tasks like placing, stacking, reorientation, and we demonstrated those capabilities with a full stack robotic system with real objects that were never seen beforehand. But we didn't solve everything. So this first part has made several assumptions that limit both the generality and the success rates when we try to run this in the real world. And I particularly want to highlight these bottom two assumptions, that objects remain fixed in the grasp and that we can just plan and then execute trajectories in open loop. And here I'm going to show some failure videos where these assumptions were violated and that caused execution failure. So here's like one example where there's just this really, really tiny prediction error and then the open loop trajectory just fails even though it's just a few millimeters away from the rack. Or here's like a motion plan that causes the arm to bump into the rack when it was going to try to do the hanging, and then that causes the mug to fall. Here's a grasp book, and the book is going to bump the table on accident, and as a result, it moves in the gripper. So it ends up misaligned with the shelf, and the robot has no idea. And in this last one with doing the can stacking, the prediction was great, and the stacking was actually done perfectly. But again, just sort of ignoring what's actually going on in the scene and playing back something open loop, when it returns back home, it kind of knocks the can over and undoes the successful stacking. So better planning algorithms, better feasibility checking between grasped objects and environments and the arm will definitely help here, and I'm really excited about a lot of the work that's being done in that area. But this also points to a more fundamental issue with doing all these tasks open loop. So this final year of the PhD has been about trying to close some of those gaps by improving the online execution ability in these tasks. And we specifically want to enable the robot to close the feedback loop so that sensory feedback obtained during task can allow more robust, reactive, and reliable performance. What we want to get out of this is something we call a visuomotor policy, represented here by pi, that again takes as input sensor observations and maps these to a distribution over robot actions, such as where the gripper should move. But the difference is now we want to run this policy at a higher frequency, like let's say 10 times per second, so that it takes in very recent sensor data and reacts quickly when things change in the environment. An approach that's quite popular and powerful for getting this kind of reactive policy these days is to perform large-scale reinforcement learning in simulation. I don't have time to get into explaining reinforcement learning right now, maybe given the time constraints, but simulation-based RL has powered some of the most impressive new capabilities in control of robotic systems like quadrupedal locomotion, bipedal robots, high-speed drones. So all these videos are not mine, these are from other people who have done really amazing work using RL. And so it's quite natural to consider if we can apply this to our setting of manipulation and rearrangement. But there are some things that make this difficult if we want to directly apply that recipe to manipulation, especially if we want to use the same recipe for a variety of tasks. Some of these challenges include exploration in tasks with sparse rewards, transferring vision-based policies from simulation to the real world because perception data just looks really different in sim and real, and even just the large effort that's typically required to create the simulation scenes themselves, getting digital assets and laying them out in a realistic way and things like that. So here I'm going to talk about a system-level approach that we've been taking that combines a few other tools alongside the core RL algorithms to help overcome some of these hurdles. One key addition that alleviates some difficulty is to combine reinforcement learning with behavior cloning. So with behavior cloning, or BC, we simply train our policy to mimic a data set of actions collected beforehand from an expert. And while this idea of combining BC and RL is really quite mature, advancements in behavior cloning have been at the core of many of the most recent advanced robotic manipulation capabilities that are being developed. So we want to both take advantage of and build on these advancements by revisiting different ways BC and RL can be combined. We'll also include a few other ingredients, like real-to-sim scanning and co-training policies on both synthetic data from simulation as well as a small amount of data from the real world. We've been exploring how to combine these components in two complementary projects. Each one instantiates a version of this framework in slightly different ways and focuses on distinct aspects of the problem. And I want to call out that these were led by two incredible master students, Marcel Tournay and Lars Ankila. It's just been the biggest pleasure working with you both this past year, so thank you for all your help in these projects. So I'll first expand on how we use these components in the context of our first system called Rialto. Our setup, as I said, we want to learn this visuomotor policy that operates online. We'll still assume objects are rigid and have 3D point clouds, but we no longer make any more assumptions about objects staying fixed in the grasp or having segmentation or doing anything open loop. So now I'll go through how each of these components comes together. So as I said, the first difficulty is how do we even create the simulation scene? Oftentimes it's quite tedious and laborious to go find a bunch of assets or make them yourself and then place them in the scene in the way you want, and then maybe that doesn't match your real world. So instead of this, we'll have a user first scan the environment where the robot will be deployed to try to obtain what we can think of as a digital twin, which can be used in the simulation. That scanning can be done with apps that are available on iPhone or Android, or of course using your latest NERF or Gaussian splatting reconstruction method. It actually did turn out to be important to use a NERF to export a mesh when we wanted to do this scanning with a dish rack, which has like really fine, thin geometric structure that couldn't be seen by the apps. And here I'll just go back in the video. So then after we have our textured mesh, using this browser-based graphical interface made by Marcel, the user can then do a little bit of processing on the mesh to separate objects that move independently from each other or separate links that need to move relative to each other. And then they can add joints, such as like a revolute joint that's being added to this door of the toaster oven, so that those links can be articulated in the simulation. And then we'll specify some very approximate physical parameters, but these don't need to be super accurate. Then on the side of combining BC and RL, the user collects a few demonstrations and trains sort of like a baseline behavior model with behavior cloning. Then we can import those assets that were obtained from the scanning procedure into a simulator like Isaac Sim and do large-scale reinforcement learning to improve upon the BC policy rather than having RL try to learn from scratch. And we make standard policy gradient reinforcement learning algorithms work using just this very simple sparse reward function that's given at the very end of episodes, indicating when a goal has been reached. And that's possible because we initialize with that imitation learned behavior, which achieves non-zero success rate. So that really is critical to get RL off the ground. That process is made fast because it uses information that's available in sim, but not in the real world. So to transfer behaviors learned by RL to policies that can work with real sensors, we follow a pipeline that's quite widely used called teacher-student distillation. And this process again uses behavior cloning, but now instead of having expert actions come from, let's say, a human demonstrator, the expert is the RL policy that's been trained in simulation, but it operates on privileged state information. So we want to sort of clone the actions taken by that expert RL policy to a student policy that operates on vision. And the final way here that BC is playing an important role is through an auxiliary behavior cloning loss that we use during the RL training. And this keeps the policy from deviating too much from the demonstrated behavior. So here's an example of what happens if we don't use this. What we find is that the RL policy can discover strategies that might exploit inaccuracies in the simulator or kind of things that were imperfect with the mesh that we scanned, let's say, like opening this door by sort of hitting it from the bottom. And these would just be things that don't really work if we try to transfer them in the real world. So BC and RL is coming together by providing a prior that improves the ability to handle exploration with sparse rewards. It's helping distill state policies to vision policies, and it's helping constrain the behavior from deviating too much and becoming non-physical. Then we'll randomize different aspects of the environment to improve the robustness to clutter and different layouts of objects. And finally, when we train that student policy that is meant to run in the real world, we'll co-train the policy with a combination of the rollouts obtained in simulation as well as a few demonstrations collected in the real world. We find that that combination really helps improve the transferability from sim to real. So here's some videos of kind of a lot of things going on. These are all policies that were trained using this procedure, running in the real world. And they're robust to all kinds of things that were just never shown in the demonstration. So background visual clutter, pretty dramatic changes in the layout of objects, Marcel coming in and perturbing things online, and like with the book on the shelf example, it can actually handle the case that I struggled with, where it adjusts the angle to try to account for the movement. So that's what that enabled. And these results really opened my eyes to the power of obtaining these controllers with this combination of simulation, RL, and these other modern tools. I had kind of been like avoiding RL for a while because I didn't think it was going to end up being super useful in these kinds of tasks, but it turns out that that combination really can supercharge it. So in this last project that I'll discuss, we explored how we can push it even further. Our setting remains largely the same, except now we have the robot operate from RGB images instead of 3D point clouds. And we also wanted to focus on tasks requiring more precise actions like insertion and screwing. And these would be the kinds of things that might be needed for robots to perform like fine-grained assembly. Here's a quick snapshot of the images that the policy sees, coming from a front camera and a wrist-mounted camera. And these assembly tasks are borrowed from this really cool task suite proposed in last year's RSS called Furniture Bench. And I'll note that for those tasks, we actually had CAD models available that they had provided for simulation. So for those, there was no real-to-sim scanning, but I can quickly show at the end some preliminary results using the same approach with reconstructed meshes. And the main takeaway is that the pipeline, with many of the same components, but with a couple things swapped out and improved, can produce policies that can perform these various kinds of precise assembly tasks while operating directly from RGB images instead of point clouds. So here's a task of inserting this leg of a table into the hole of the table and then kind of screwing it into place. And here's another example from the task suite called Lamp, where it sort of has to pick up this bulb. Here we see it tries and then it tries again. So these were policies, again, trained with a combination of simulation and real-world data, where we used the real-world data to try to kind of reduce the gap between what the RGB images look like in simulation and what they look like in the real world. So just very briefly on how we get the higher precision capabilities. Those are enabled by some innovations on the policy learning side. First, we incorporate diffusion policies and chunked action predictions. These provide a stronger BC method for learning the prior behavior from demonstrations. And we found that that combination of both action chunking and diffusion were really beneficial for getting that initial success rate off the ground, which is critical if we want to use sparse rewards. Then we'll train a Gaussian residual policy with reinforcement learning, and this provides local corrections on top of the frozen base policy's actions. So here's some examples of abilities discovered by the residual, again, trained purely with RL and a sparse reward function. And the residual here is going to dramatically improve beyond what the base behavior could do. So first, we'll see some quick examples of the robot doing a successful insertion despite the part moving in the hand like a lot, and the robot using this grasp that was never seen before in the demonstrations. And there will be one more example here. Again, it's like grasping at this tilted angle that was never done, but it can still figure out how to do an adjustment and get the insertion right. That was a really common failure case of the pure BC policy. And then in the second example, it figures out how to adjust the leg location and sort of prevent it from pushing down until it's really like over the hole, and only when it's over the hole does it kind of proceed with the screwing. So as I said, still working on.
Just one quick question. Can you say something about the frequency at which that residual policy is running and the output of the policy, the output space?
Yes, yeah. So the policy operates at 10 hertz, and the chunks are predicted at a slower frequency. So we have the base policy predicts a chunk of, let's say, 8 actions, but then the residual policy is going to make predictions at every one of those steps for each of those actions. And its output space is sort of a shared normalized action space that is sort of, it's the same normalized action space that the base policy operates on. So the way we treat the residual actions is as like a delta that we can just directly add to the base policy action. And we scale it down. We do some stuff to like scale down the magnitude so that it's kind of aligned with this inductive bias of being more of a local corrector that can't like completely overwrite what the base policy was trying to do.
But it's feeding a position controller or some impedance controller, like what's running on the robot?
Yeah, the robot is running a joint impedance controller with like moderate stiffness and moderate stiffness, so like close to position control but with some compliance. And we're on top of that running a differential IK controller. So the policy outputs absolute end effector poses, which we then send to the diff IK, and then that gives us joint targets. Cool. So as I said, still working on the final piece showing RGB-based real to sim and sim to real, but getting some preliminary results with the pipeline on my favorite mug rack task as well, and those are scanned from the real world. And we've also recently applied the method to an insertion task that has even higher precision requirements. The behaviors are a little jerky, but the tolerance between these two parts is like a fraction of a millimeter, and the process can still work to take the initial success rates from BC from like less than 5% to over 90%. Okay, so I'm wrapping up. Overall, these projects have contributed pipelines for making RL easier to use in tabletop manipulation and rearrangement. And we showed that those pipelines unlock new levels of robustness and reactivity across a range of both rearrangement and higher precision assembly tasks. And I'm definitely not the first to make these points, but I think that these results are also kind of a valuable reminder of the ways that reinforcement learning and data from simulation can be highly complementary to, let's say, pure behavior cloning or learning from data collected purely in the real world, because these are things that are pretty popular and widely used right now. But I think throwing it all together is going to be like strictly better. So I'll pause for a sec if there's like any questions, but I guess we're maybe running short on time. So if there's no questions, I'll go forward with some acknowledgements. And of course, feel free to leave if you need. It's 11. So, sorry?
You made it in 11.
I know, I guess I spoke fast. I didn't mean to. Hopefully I didn't speak too fast. Okay, so time for some acknowledgements. What a journey. My advisors that you all met this morning, Pulkit Agrawal and Alberto Rodriguez, working with the both of you has just been beyond incredible. You both bring such an amazing combination of insight, intuition, and experience across robotics and machine learning, and as well as communication and writing and presenting. I've just learned so much from both of you over that kind of whole breadth of areas. So one thing I'll always appreciate from Alberto is how he would say, of course you want the work you do in your PhD to be high quality and impact the field, but remember that the main product at the end of the PhD is not really the work you do, it's more you, the person who's sort of gained a set of experiences and skills and things that you can bring with you forward in whatever you do next. So thank you for always kind of helping me keep that in mind. And with Pulkit, just learned so much about clear thinking and clear writing and iterating on ideas that are vague, or a piece of writing that's a little messy or that I think is clear but that other people might not, or something you're stuck on, just until it becomes clear and feels intuitive and simple to understand. I think you kind of have a really deep ability to do that and bring that out of others, so thank you for teaching me that. And yeah, you've both just provided a lot of support in the environment to do research. You've encouraged me to explore stuff that was kind of new to me when I started out, as Pulkit said, and collaborate with lots of people and have fun, but while also pushing myself to learn how to be a researcher. So thank you both for allowing me to craft this experience in a way that made it really feel like it was mine. Okay, and then my committee members, Tomas Lozano-Perez and Vincent Sitzman, I want to thank you both a ton. So with Vincent, we worked together very, very closely on the NDF project. And that was really one of the most exciting and valuable experiences of my PhD and maybe my life. It was quite an undertaking at the time during COVID. And I just learned so much from working with you and appreciate how formative that project was and that period of time was in shaping the rest of the direction that I took my PhD. And Tomas, your work going back to motion planning and task and motion planning with Leslie have just from day one shaped the way that I think about what components we should have in a robotic system. And it's been a massive privilege to get your advice and insight and support at various points throughout the PhD. So thank you both. Some other academic mentors that I just want to call out and acknowledge, Leslie Kaelbling and Andrea Tagliasacci. We also worked together on some projects, had really valuable conversations about projects and research directions, and I've also learned an immense deal from the work that you all have actually done yourselves as researchers. So thank you for that. And Russ Tedrick, I TA'd with Russ for his manipulation class. Want to thank him for taking me on. That was an amazing time. Helping conduct the class and just teaching that material really helped consolidate what I had kind of been haphazardly teaching myself for the prior years before that. Then I want to thank Lucas, Ankit, and Dieter. Those were mentors during my NVIDIA internship. They helped a lot with the RPDiff project and helped it just be a really great summer in Seattle, getting to experience a different research style and environment. And then finally, I want to thank Yenchen, Bamjun, and Yulin. You guys are just super influential on my research direction, and I learned so much about computer vision and machine learning and planning and being, rigorous in research. And it was an amazing time collaborating on projects, and we had so many valuable chats over the years, and you'll always be people I really look up to. Also want to thank the folks who allowed me to try to teach them something. The MNGs and master students and UROPs that I got to work with over the years. One of my major goals from day one was to try to kind of pay it forward and impart some of what I've learned about robotics and research to others. And that was just such a privilege and a pleasure to work with you all. You're all brilliant. And I'm so excited to see the awesome stuff that you keep doing. So thanks for taking a chance on allowing me to try to teach you something, and I hope you gained something positive from it. Too many individuals to thank here, but Improbable AI Lab, MCube Lab, the EI community in CSAIL, really amazing times in the lab and on retreats and out at dinners and traveling to conferences. In addition to lab mates like staff members, Lisa and Marcia and Fern and people that help with the logistics of getting research done. It was really crazy times starting out with COVID and coming out of COVID and moving buildings, and I just learned a lot from all of you over the years. I always felt welcome and supported, so thank you all for creating a really positive research environment and community. Okay, and then on the personal side, sorry. 1 second. I want to thank my parents and my family. Some of you all are here, and thank you all for coming. I just owe you everything and supporting me and teaching me how to care for myself and how to believe in myself, how to push myself. So I love you all, and thank you all for being there for me over the years. My friends, roommates, support system in the area, we had a lot of fun. You all really helped me de-stress and remind myself to enjoy life along the way, not get too wrapped up in whatever work stuff is going on. So thank you all for being amazing friends, making home feel like a place of relaxation and fun and happiness. I really appreciate that. And finally, Zoe, thank you for your support and patience, for all the fun, silly experiences, lounging and traveling and dancing and talking about food. And thank you for helping me edit many of my papers. You really came in clutch getting the page limit, getting within the page limit multiple times. And being with you has just transformed this experience of coming here for my PhD into something much, much bigger and more meaningful than I ever thought it would be. So with that, thank you all for listening. It's been a pleasure, and we're 7 minutes over, so I guess that means I talk pretty fast, but happy to take any questions. I don't know if we should put a cap on how much time it takes, because I think there's someone else is going to take the room at 11:30, apparently.
Okay. So time for questions.
So for this mug hanging task, suppose one of the rack things were pointed downwards. Would it be able to figure out that would be a bad thing to try to hang a mug on and that it would slide off?
No, yeah, right now it would think that's perfectly fine. So I think that points to one of the issues with incorporating equivariance is that you don't always want equivariance, depending on the semantics or other constraints of your task. And so for dealing with issues like that, you would want to combine it with some other kind of, ideally in that case, I guess, like physics engine or something that can simulate forward what will actually happen when you do that placement and realize that, oh, it's going to fall. So we're not able to handle that at all right now. So that's exactly why I could do like the sideways, the placement of the bottle in the sideways container. It doesn't know that that's a nonsensical thing to do.
That makes sense.
Yeah.
At the back.
Oh boy.
I'm kind of in the human field, so do you think this approach to training machines through mathematics, shape formation and so on, is the way to eventually train machines for other tasks, such as error prevention in decision making?
Yeah, so the question is about when we train machines or robots to do things, is that gonna naturally lead to safe behavior or like detecting errors online or being able to prevent errors occurring when, you know, let's say a scenario's never been seen beforehand. So this is one of the most widely discussed issues, I would say, of using learning-based techniques, is that within some distribution, they can perform and behave in a somewhat predictable fashion, but that if you go outside the distribution where they've been trained, they really can sometimes behave kind of arbitrarily badly. And so there's definitely a lot of work that needs to be done on understanding what are those boundaries, understanding how to characterize them, and have like more like higher level systems that can detect when maybe something's going wrong. Those detection systems themselves can also be learned from data, but I guess, yeah. So the simple answer to the question is no, there's no sort of direct, easy solution to getting safe, predictable, sort of never makes an error or can detect its own errors behavior out of these systems when we take learning-based approaches.
Hi, so the paper with the like the pose diffusion, if I understand correctly, in your like denoising process, your noise is like small SC3 transformations, right?
Yes.
So how does this compare to like more maybe like a more standard thing in vision where it's like a Gaussian noise?
I see.
Perturbation?
Yeah, so let me just pull up the slide. So you can still kind of construct distributions over the SE3 space. So we can have some, let's say, distribution over Euler angles, and those would be what we sample from to construct these transforms, which we then apply as the perturbations. I guess the way that we apply the noise, because in this case we wanted each of the noise like intermediate steps to correspond to like a valid transform, we can't apply it in like a, let's say, purely additive way. I think in normal like image diffusion, you sample Gaussian noise and then you just directly add it to like pixel values. Whereas in this case, we can do that for the positions, but for the rotations, we need to think about the manifold structure of rotations. But we can still construct kind of various noising distributions. Those can be Gaussian, it could be uniform, it could be have some other noising schedule, kind of whatever noising schedule we want. We can still apply it in this space of rigid transforms.
Why does it matter that the intermediate ones are valid transforms? Like, is it not okay for that just at the end?
It doesn't necessarily matter. There's other work that does kind of similar denoising or denoising to produce a final pose at the end of at the end of a denoising process, but where all the intermediate iterations don't necessarily themselves correspond to like valid transforms. This was kind of a choice that I made early on based on some intuition that like maybe it's useful to actually show the model the intermediate configuration of the object relative to the scene in point cloud space. And to get that, that means that we want to actually turn each of those noise steps into a transform that we can apply. The other way to do it, we wouldn't really be able to interpret or like show visually what those intermediate noise steps look like. But I think it could work the other way too. Yeah.
This is probably in the context of how many bits, bytes, and nibbles does it take to change a light bulb, but when I was looking at all this complex movement, one of the questions I had was, do you feel that is computing power a limitation to much more complex activity and actions taken by the mechanism, the robot that you're using? I'm just kind of curious as where computing power provides a kind of a ceiling in terms of what you can do.
Yeah.
Is that out there, or is the computing power still so far beyond?
No, it's a relevant constraint depending on some details of how your system is set up. So, for example, when we have these neural networks, we want to try to run them as quickly as possible if we want to do some, let's say, real-time control process. But in these examples, anytime I said the word denoising or diffusion, that process actually involves running the neural network procedure many, many times to construct the final answer. So to be able to run that multiple times just to get a single solution, and we want to run that whole process, let's say many times per second, then compute is definitely something that can make a big difference. In training these models in the first place, that's definitely an area where people constantly think about compute and sort of getting as much performance out of the computation as possible to try to make the neural networks bigger and bigger, or train it on more and more data and get that process to converge more quickly. And so that's a bit different. That's more about the offline procedure of getting the neural network in the first place versus running it online to get these really intricate motions, as you're saying. But so I think short answer, yes, compute can make a difference. And if we can run things faster, that can enable sort of longer horizon look ahead and more sophisticated motions and more reactivity just by being able to be faster. Yeah.
So we have time for just one short question. Anyone?
Thanks for the great talk, Anthony. I was wondering about the RNDF work. You mentioned that you have to have a separate NDF per object category. I was wondering, what's the limitation for basically just like training one NDF model over multiple categories of objects and then just using the demonstration to
So like encode some like multi-class NDF model or multi-category NDF model and try to have it just infer like the relevant part irrespective of what category. Yeah, so we had some tests where we kind of did this for training one model on bottles, bowls, and mugs. And it kind of still works, but the main issue that we found that can sometimes happen is if one of those categories is kind of like simpler than the rest, it can end up dominating the way the representation is sort of like biased. So the example for that we saw is when we train on both mugs and bowls, and then we do our whole process of querying, let's say, the handle and trying to detect the handle. We found that the model trained on just mugs was a lot better at finding handles, whereas the model trained on bowls and mugs was kind of worse at even reconstructing handles, and it was much more biased to just thinking that all mugs were bowls because it was just like simpler for the model to learn that.
And maybe also they have like mugs and bowls have similar geometric features other than the handle, so it's just seeing that a lot more.
Yeah, exactly. I don't think it's something you couldn't do. I think maybe adding like an additional conditioning variable that's just one more input would also probably be fine for that, to have it be more explicitly represented that there's different categories but still the same set of weights. I think that would probably also be fine.
Thanks.
So let's thank Anthony once more for the